Hello, I'm Yohei Sawada from the University of Tokyo, Japan. So since it is the midnight in Tokyo, so I would like to perform this presentation as this recorded talk, but maybe I'm here. So if I successfully stay up, so please feel free to post any questions. I would like to answer them in the real time. So random reanalysis is the special temporary homogeneous dataset of land surface variables such as soil moisture, temperature, fluxes, and vegetation. There have been many existing land reanalysis datasets. They are provided by driving a land surface model in the offline manner, decoupling the atmosphere. Our motivation is that most of them have not solved terrestrial ecosystem explicitly, and the integration of long-term microwave satellite observation has not been fully exploited. So we would like to develop a new land reanalysis dataset, including a terrestrial biomass based on the AMSR E and AMSR 2. And this is the 20th anniversary of AMSR 3 satellites, starting from the AMSR, which was succeeded by AMSR E onboard Aqua, and JAXA launched a new GCOM-W AMSR 2 satellite in 2012, which will be succeeded by AMSR 3 next year. So this long-term observation is quite beneficial, and it can be expected to further continue in the future. And in this slide, I would like to briefly explain what we can see in AMSR 3 satellite, because it is a bit different from the well-known L-band satellite observations. So C-band brightness temperature is sensitive to both vegetation dynamics and soil moisture as L-band. So we have performed these kinds of long-term ground experiment, and these figures are the summaries of that. So the center figure shows the relationship between the microwave signal polarization index and vegetation water content. So we can see clearly that we can observe vegetation water content up to 2.0 kilogram per square meter. In other words, it is a bit difficult to get the BWC larger than 2.0 because they have no sensitivities to BWC if the BWC is larger than 2.0. And also, this is a summary of the 5 different crop types or vegetation types. And most of these variability can be explained by the soil surface roughness, not the vegetation structure. So we have small species dependency to the microwave signals, which is a quite good news. So C-band is long enough to mostly neglect the small differences of the vegetation structures. Okay, and the right figure shows the vertical axis shows the microwave sensitivity to the surface soil moisture as a function of vegetation water content. So there are huge sensitivity to the soil moisture in the bare ground, but the vegetation water content approaches to 0.5, this sensitivity almost vanishes. It is a bad news actually. So we can sense soil moisture with bare soil or sparsely vegetated area. So which is a limitation of C-band, and that we would like to overcome by L-band satellite observations. So the goal here is, once again, the goal is that to develop the new land reanalysis, which is called the Ecohydrological land reanalysis, or ECLA, based on the integration of AMSR series satellite observation and the land surface model. And there are the configuration or characteristics of ECLA. So ECLA is a land dataset after 2002. ECLA includes vegetation water content and reef area index, as well as any other conventional land variables, which is the most major characteristics of this ECLA. And ECLA is a semi-global dataset, which includes snow-free and moderately vegetated areas. And ECLA will be publicly available in 2023, next year, from the JAXA's website. So we are now working on it. Right? So ECLA is generated by our coupled land and vegetation data assimilation system, or CLBDAS. So CLBDAS has some land surface model, and the characteristics of this ecohydro ship is that we can simultaneously solve the terrestrial water and vegetation. So we can solve the carbon pool dynamics inside the model. And also, as the observation operator, we have a radiative transfer model in the microwave range to directly assimilate the brightest temperature into the model. So we didn't use any retrieved product. Instead, we performed a direct assimilation of brightest temperature. And all state variables, including vegetation states, are adjusted by particle filter. So as I said, the brightest temperature is sensitive to the vegetation dynamics. And we solve the vegetation dynamics so that we can directly adjust, and we can directly and objectively adjust the vegetation biomass using the particle filter. And in any ensemble systems, the ensemble split is quite critical. And our system, in our system, the ensemble spread is maintained by the mutation of particle by sampling the covariance of the background. And also the ensemble spread is maintained by perturbed meteorological forcings. So each ensemble has a bit different meteorological forcings by perturbing the original meteorological forcings, such as rainfall and radiation. And this slide demonstrates some results of the data assimilation as a case study. So left figure shows the dynamics of leaf area index. Gray lines are the open loop ensembles, the ensemble without data assimilation. And the blue line is the result of the particle filter. So we can significantly reduce the uncertainty of our simulated leaf area index. And the right two figure shows the time series of the root zone soil moisture. So our hypothesis is that the data assimilation can inversely estimate the dynamics of root zone soil moisture from the signal of vegetation dynamics, because we have a strong relationship between root zone soil moisture dynamics and the terrestrial biomass, right? So although the satellite can only see the above ground vegetation, but we can inversely estimate the root zone soil moisture dynamics if the root zone soil moisture and vegetation dynamics are tightly coupled. So, although the C-band microwave observation information is limited, but we can expect that we can improve the entire root zone soil moisture profile by our data assimilation system. And in the ECRA, we need to disable the parameter optimization function, but we perform the state variable adjustment in the every single day using the AM3 and AM2 brightness temperature. Okay, and let's move on to the technical validation of ECLA. So this is the ECLA vegetation dynamics against MODIS LAI. So note that MODIS LAI is not assimilated in our system. So MODIS LAI can be the independent observation of the vegetation dynamics. And the left two figure shows the unbiased RMSE and the correlation coefficient. And the left two figure shows the differences between the ECRA and the open loop without data assimilation results. So we can see it clearly that in the unbiased RMSE, we can improve the representation of the variability of vegetation dynamics in almost everywhere. And if you look at the correlation coefficient, also we can see many improvements, especially in the vegetated area, although we have some degradation in the deserted area. Okay, so that's the good news. And this slide shows the surface soil moisture against ESA CCI combined satellite retrieval dataset. So if you look at the unbiased RMSE, although we have some hot spots of the degradation, but almost everywhere we can see the improvement of the variability of the surface soil moisture. So this is also the good news. And although it is not the official product, but I also evaluated the representation of the fluxes, such as the gross primary production or GPP, against the in situ flux site-based machine learning product, Fluxcom. So yeah, although we have some degradation in the unbiased RMSE, such as India, China, Southeast Asia, and other regions, but if you look at the correlation coefficient, we can see the improvement in the almost everywhere. It is because as I shown you, the vegetation seasonal cycle of vegetation has already been improved by the data assimilation, and it leads the improvement of the seasonal cycle of the GPP. However, the absolute value or absolute variability of the GPP cannot be improved by data assimilation, probably because the absolute value of GPP is determined by the model physics or model climatology, which cannot be directly improved by the state variable adjustments. right? And this is a point scale evaluation at the Australian supersite. So in this kind of supersite, we have the in situ observation at the subsurface soil moisture, and we compare them. And as I expected, that we have some huge or large impact on the root zone soil moisture dynamics by the data estimation. However, it is technically difficult to evaluate this impact by the in situ observation. First, we have a huge biases or huge gap between the observed and the simulated soil moisture. And the second, we are not so sure that this in situ observation is especially representative in the whole satellite footprint, especially when we focus on the subsurface soil moisture. And also, it is very difficult to verify the simulated vegetation water content, but we have some in situ, some small number of the in situ vegetation water content observation, which is in the range between the 0 to 1.0 kilogram per square meter. And our estimated the vegetation water content is at least comparable. But we need to more kind of intensive observation to verify those kinds of results. All right, and let's move on to the future direction. So as I said, we need to switch off the parameter optimization scheme of our CLVDAS, but in the land surface modeling, actually the systematic errors is much severer than random errors. So the systematic errors may come from the parameters uncertainty. So we need to address it, actually. And the question is parameter optimization possible in the global range? Because in general, the optimizing parameter is time consuming. But my answer is yes. Using the machine learning based surrogate model, we can obtain the posterior distribution of parameter in several minutes for each grid. So it means that we would like to replace the responses of the parameters to the cost function by machine learning. So in that case, this machine learning is super fast, so we can apply the non-parametric Bayesian inference. And this is the example of our study. So it is possible to get these kinds of the posterior distribution of the parameters and dramatically reduce the uncertainty of the estimated referral index in just several minutes using the one node of the supercomputer. So we need to move on to that to further improve our RAND reanalysis dataset, including the terrestrial biomass. So this is the summary of my talk. Thank you very much.